The next thing we're going to investigate is sometimes referred to as the second fundamental theorem of calculus. In example 6, let's evaluate the function. We're going to define capital F of x. So this is going to be a function of x, where x is the upper limit of integration on the definite integral from 0 to x of cosine of t dt. And we're asked to evaluate capital F at several different values of x, 0, pi over 6, pi over 4, up to and including pi over 2. Well, instead of having to do several different integrals, let's actually go ahead and see if we can calculate this definite integral first, and then we'll evaluate the function once we have a closed form expression. So f of x, which is defined as the definite integral from 0 to x, cosine of t dt. So it's a function of t, the integrand is, and we're integrating with respect to t, so this makes sense. According to the first fundamental theorem of calculus, we would want to find an antiderivative for the cosine of t, which we know is going to be equal to the sine of t. We would then take and evaluate that antiderivative at the upper limit of integration. That's going to be sine of x, and then subtract the antiderivative evaluated at the lower limit of integration, which would be 0. The sine of 0 is 0, so it turns out that this fancy looking expression, this fancy looking function, is really nothing more than just sine of x. And we know from previous classes, we know how to evaluate sine at a bunch of different values. F of 0, if I plug in 0, I would get 0. Notice that this would make sense because if I had plugged that in directly up front, what this would have been equal to would have been the definite integral from 0 to 0 of cosine t dt. That was one of our rules for definite integrals, is that the antiderivative from a to a of f of t dt or f of x dx in this case would be equal to 0. If we plug in pi over 6, the sine of pi over 6, that's equal to a half. F of pi over 4, that's the sine of pi over 4. That's equal to the square root of 2 over 2. F of pi over 3 would be the sine of pi over 3, which would be the square root of 3 over 2. And then lastly, if we evaluate f of pi over 2, this would be equal to the sine of pi over 2, which would be equal to 1. So to get a sense out of what's happening here, let's kind of go back and look at the following. So one of the things we can kind of interpret is we can think of this particular function as giving us the area under the cosine function, cosine of t, from 0 to x. If I graph the cosine of function, and I'm just going to graph it between 0 and pi over 2, it's going to look something like this. This would be the graph of cosine t. The area under that curve from x equals to 0, from t equals to 0 to some unknown x value, let's call it x, that would be this right here, would be represented by the definite integral from 0 to x cosine t dt, which we're defining to be capital F. Notice that if you look at the sequence of inputs that we plugged into this function, 0, pi over 6, pi over 4, pi over 3, up to x equals pi over 2, these are values of x that are increasing, going further to the right. And what you can see is that as our x value increases, between 0 and pi over 2, we're adding on more and more and more area until we get to the area between 0 and pi over 2. That total area would be equal to 1. This is a very popular approach and a very important concept to sometimes think of this function as what's referred to as an accumulation function. One of the things that we want to notice is that in the previous example, note that the derivative of f in the original integrand with only the variable changed. Okay. So one of the things, if we take d dx of f of x, this would be equal to the derivative of sine of x. So if I take the derivative of this new function capital F, it's just the derivative of sine of x, and we know that the derivative of sine of x is going to be the cosine of x. How does this derivative of that starting function compare to the new function of x we get? Well, it looks kind of like the integrand, but with a variable change. Instead of having the variable t, it has the variable x. And that result, noticing that concept, is what's referred to as the second fundamental theorem of calculus. Okay. The second fundamental theorem of calculus, for us this is theorem 5.11, says that if f is a continuous function on an open interval I containing some point a, then for every x in the interval, the derivative of the definite integral from a to x of f of t dt is going to be equal to just f of x. It's the original integrand, but the original integrand was a function of t. The final answer will be a function of x. To give you some intuition as to why this would be true, let's go ahead and just think about how this would work. And let's suppose that we were able to actually integrate f of t dt, f of t, and let's suppose that it has an antiderivative capital F. So let's let capital F be an antiderivative for little f of t. That is that f of t, capital F, would have the property that f prime of t would be equal to, and actually let me call it f of x. Let me call it, so I don't want to confuse the integration here. Let's call it f of x. Let capital F of x be a antiderivative for little f. Then it will have the property that capital F prime is going to be equal to lowercase f. So if we think of this calculation maybe as being like a two-step procedure, just to kind of explain to you why it's true. So if I were to do this definite integral on the inside, using the first fundamental theorem of calculus, what that would say would be to find your antiderivative of f as a function of t. That would be capital F of t. We would then evaluate that at the upper limit of integration. So this would give us capital F evaluated at x minus capital F evaluated at a. Now we're going to go ahead and take the derivative. The derivative of capital F, let me just write it for a moment as f prime of x. F of a is a constant, so its derivative would be equal to 0. But because capital F was an antiderivative for little f, this thing here is nothing more than little f of x. And that will kind of help explain to you, why we still get the original integrand back, but with the change of variables. The reason is, if you were to think about using the first fundamental theorem of calculus, when you have this evaluation, that changes it from a function of t into a function of x. Okay. Generally speaking, when you apply the second fundamental theorem of calculus, you wouldn't have to show all of this in-between work. You could just go right to the final result. For example, if we wanted to evaluate the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 dt, again, we're taking the derivative of a definite integral. So according to the second fundamental theorem of calculus, we're essentially thinking of those two operations as being inverses of each other. So the basic idea is that we should just simply get the integrand back. So whatever the definite integral does, the derivative will undo it. However, we don't get a function of t, we're going to get a function of x, which is our upper limit of integration. So without doing any work, we would know that the final answer here is going to be the square root of x squared plus 1. And for us at this stage in our calculus career, that's very important because we don't quite yet have a method or a way to actually find a definite integral of this thing, or the antiderivative of the square root of, let's say, u squared plus 1 quite yet. But yet, nonetheless, we're still able to do this full calculation because we can use the second fundamental theorem of calculus. Let's take a look at another one. Let's take a look at example 8. Here we want to find, we have capital F, which is going to be defined as the derivative with respect to x of the definite integral from pi over 2 to x cubed of the cosine of t dt. Okay, so what's happening here? Well, it's very similar. We're taking the derivative of a definite integral. Our upper bound is not x this time, it's actually a function of x. It's x cubed. So that's going to modify things in a couple different ways. To actually find this is one where we can actually do in steps. And then after we do the steps, let's come back and see how this particular example generalizes that second fundamental theorem of calculus. So let's construct capital F by doing the following. We can first start off by actually finding the definite integral on the inside. The antiderivative of cosine t is sine t. We're going to evaluate that from pi over 2 to x cubed. This is going to be equal to d dx of the sine of x cubed minus the sine of pi over 2. Sine of pi over 2 being 1. And now let's go ahead and take the derivative. To do the derivative of sine x cubed, that's going to require the use of the chain rule. Derivative of sine is cosine. Leave the inside function alone. And now we need to multiply by the derivative of x cubed, which is 3x squared. Derivative of a constant is 0. So we get as our answer 3x squared times cosine x cubed. Okay. How does that compare to the thing that we started with? Again, if this had just been a simple bound of x, then the answer would have been the cosine of x. But we didn't have a simple bound of x here. We had a bound which was a function of x, namely x cubed. What did that do to our final answer? Well, the answer is this. Our final answer was the original integrand, which was cosine, evaluated at that upper bound, evaluated at x cubed, and then from that, we have a chain rule application where we now need to multiply by the derivative of that upper bound, which was our 3x squared, and that's what's going to give us the final answer in this case of 3x squared cosine x cubed. The same work we just kind of showed you a moment ago in terms of describing the steps of this thing. If I define, let's say, if I wanted d dx, let's just do this in more generality, of the definite integral from, let's say we still have a fixed lower bound, constant a, and instead of having a simple x up top, let's suppose that our bound is u, which is a function of x. And we'll still think of this as little f of t dt. If I am able to find a antiderivative for little f, we'll call that capital F of t, that would now be evaluated from a to u, which would be equal to d dx of f evaluated at u minus f of a. This is our chain rule. It's simply the derivative of the outer function, leave the inside function alone. But then because u is a function of x, you would need to multiply by du dx, and then minus 0. So what is the takeaway from this? If you want to call this a generalized, and of course little f here, I should say, little f prime of big F is just little f. So what do we have here? If you have the following, if you had the definite integral from, let's say, a to u of x f of t dt, and if we're taking the derivative of that, the derivative with respect to x, how do you evaluate this? Well, it's simply the integrand evaluated at the upper limit of integration. But then from the chain rule, because the last thing we're doing is taking a derivative, you then need to multiply by the derivative of that upper limit of integration. If you want to, you can generalize this even further. We're not going to do this in our class, but it's possible instead of having just simply a variable upper bound, you could even have things like a variable lower bound as well. So in even more generality, just for food for thought, let's call this w of x, let's call this u of x, f of t dt. A more generalized version of the second fundamental theorem of calculus would say the following. The answer to this would be because we're doing the derivative of a definite integral, we're going to end up getting the original integrand, which is f, evaluated at the upper limit of integration. From the chain rule, I would need to multiply that by the derivative of that upper limit of integration, which would be u prime of x, minus, again, thinking along the lines of the first fundamental theorem of calculus, the original integrand evaluated at the lower limit of integration, and again from the chain rule, then times the derivative of that lower limit of integration.